Hello and welcome to the third tutorial in this mini-series at the higher maths level on exponentials and logarithms. Now in this tutorial I'm going to be speaking about a number, which sounds a bit strange at first, but there is a very special number that you will get to know which is crucial in the study of exponentials and logarithms, and in fact this number has a ubiquitous role in the whole of mathematics. And let me just tell you the name of this number. It is commonly given the symbol E and is sometimes known as Euler's number. And Euler was a very distinguished German mathematician from a couple of hundred years ago. Euler did not discover this number, but he was one of the first, I think, to recognize its importance, and he used to use the symbol E for this number, and this symbol has been used ever since in honor of Euler. So, what is it about E? Well, remember we, in the last couple of tutorials, have talked about the exponential function, and I've always written it as y equals a number raised to the power of x, and we have spoken of this number a as the base of the exponential. And in the first tutorial, when I was motivating the exponential function, I was looking at a doubling, and very naturally that base was equal to 2. So we were looking at the number of bacteria over different generations, and that number increased as a power of 2. So the number of bacteria was 2 raised to the power of the number of generations. Another common value for the base is the value 10. And that's really comes from scientific notation that we often like to express either very large or very small numbers using a base of 10 in scientific notation, and that's because it's very easy to utilize in our decimal system. So scientific notation uses the base 10. Now you're free actually to use any base you wish. We tend to just place the restriction that a is greater than 1. I mentioned that if you somewhat perversely chose a less than 1, then you could relate that to a decaying exponential. So we tend to use a value of a base that's greater than 1, and really any number you wish could be used as a base. However, here's the interesting thing. Probably in about over 90% of applications of exponentials in mathematics and in science, we do not use 2 or 10 or any other number for the base except for the particular number, choosing the base a equal to e. We choose this number e to be the base. And that might seem perhaps mysterious, particularly when I tell you what the value of e is. What is the value of e? Well, I can tell you first of all that e is an irrational number, so it's not an integer, and it's also not a rational number. It cannot be expressed as the ratio of two integers. It's an irrational number. It's also what's called a transcendental number, meaning it can't be found as a root of a finite polynomial. And another famous transcendental number is pi, which is an irrational transcendental number. So e, although not really having any obvious relation to pi, is a similarly sort of enigmatic number in that it's not a root of a polynomial. What is its value? I hear you cry. This is its value. Because it's irrational, if we write it as a decimal, the digits will go on forever. And let me just write down the first several digits here. So it's 2.7, and then a repeating set that must have led people early on to think that perhaps it was a rational number, 1828, 1828. Although I suspect it was known to be irrational before people could work out this level of precision. But then those repeating digits cease, and we just have some, apparently somewhat sort of quasi-random digits as you get in these type of irrational numbers. So it's 459, 0, 4, and then ... just goes on forever. And this number has been calculated to millions or probably billions of decimal places. So obviously there's nothing about this particular set of digits that would lead one to think, well, this must be a very special number. Instead, let me show you mathematically a way that we can define this number e, and that will start to give you a little inkling into why it might be special. But actually, the reason that it's so commonly used in science is ultimately because it has a very special property when you express an exponential in terms of e. So when we write y equals e to the x, when we choose that base to be equal to e, it turns out that the exponential function written in this fashion with a base of e has many beautiful properties when you are performing calculus. I won't say what those properties are right now, but after I finish this Exponentials and Logarithms mini-series, I will give a tutorial on the calculus of the exponential function, and you will see then very clearly why e has such a special role as the base of the exponential. So let's see, how can we get a handle on this number e? Well, it turns out that e has some beautiful ways of being expressed mathematically. Let me just show you one that I'm not going to talk about in more detail, but just to give you an example. So one way that you can express e is as the following infinite series. You can write e equals 1 plus 1 plus 1 divided by 2 plus 1 divided by 3 times 2 plus 1 divided by 4 times 3 times 2 plus 1 divided by 5 times 4 times 3 times 2, and so on. You can easily see the pattern there. There's an infinite number of terms, and indeed, if you add up all these terms, you exactly get the number e. These things in the denominators here are called factorial numbers. You would meet those at the advanced higher level, but for our example here, you can see very clearly how you would extend this series on forever. So that's a famous series representation of the number e. Let me show you, though, a different representation of e, which really harks back to its origins, how it was first discovered. I believe it was by one of the Bernoulli brothers. The Bernoulli brothers were famous mathematicians of the 1600s, and I believe it was one of the Bernoulli brothers that discovered it through thinking about compound interest in finance, and that's where this representation of e comes from. You can represent e as the following: 1 plus 1 over a very large number that I will represent as n, all raised to the power of that same very large number. So in other words, you choose a very large number, let's say 100 or 1,000 or 1,000,000, take 1 over that, you add it to 1, and then this number you multiply it itself a number of times equal to n. And if you do that for very large numbers that ultimately tend to infinity, so essentially if you make that very large number become arbitrarily large, you will end up with exactly the number e. Let's just show that that's true, because that's not obvious, right? So let's just choose a largish number. Let's take 1 plus 1 over that largish number. I'm saying largish because I'm going to do this on a calculator. Obviously, I will not be approaching infinity for the size of n, but you'll get the idea though very quickly from this. And then let's take 1 plus 1 over that largish number raised to the power of n. Let's just see. There's nothing like just seeing what happens when you do this sort of thing. And let's choose for n. We want something fairly large. Let's start with 10. Let's then do 100. And then 1,000. Let's then do 1,000,000. I'll write that as 10 to the 6th. And let's do 1,000,000,000. And let's just see how we get on with those numbers, okay? So obviously, if I take the number 10 and take its inverse, I get 0.1. And if I add that to 1, I get 1.1. No surprises there, hey? Now what I'm going to do is take this number and multiply it by itself 10 times. So on the calculator, I can raise this to the power of 10. And that's interesting. You see, I get a number that is, not too far from this number we've been talking about, this curious number e. So this gives me the number 2.593, and I'm just going to say ... there. Now, with 100, take the inverse, add it to 1, I get 1.01. Now, obviously, I could just write these down straight away, but I want to show you sort of mechanistically on the calculator what we're doing, so you get a very firm idea of the procedure here. And then multiply this number by itself 100 times. So I raise this number to the power of 100, and I get 2.704 ... Let's repeat this with 1,000. So 1 over 1,000, add it to 1, multiply it by itself 1,000 times, so raise this to the power of 1,000, and you see we are apparently drifting towards this wonderful number e here, which is just here for your reference, 2.718281828. So here I have 716 ... Now when I sort of leap now to a much bigger number, I'm going to do 1,000,000 here, which is a bit awkward to write. 1.000001. So 1,000,000, I can just write that as 1 exponent 6. 1 over that, add it to 1, and raise it to the power of 1,000,000. I get, wow, you see we're, for such a big jump now to 1,000,000, we're getting quite close to this number. So 1,82804 ... And finally, just for fun, let's just do 1,000,000,000 here. So 0.000000001. That is 1,000,000,000 inverse added to 1, and then I'm going to raise this to the power of 1,000,000,000. Multiply this number by itself 1,000,000,000 times. And we have 2.718281822, and I think let's just put ... there, because the calculator display is essentially full now, and so we shouldn't really trust that last digit there. So if you were using a computer and writing your own code, you could do this for much bigger numbers if you're being very careful with the precision of the numbers, and you would be able to start to access these higher digits in the decimal representation of E. But what you can see from this little just demonstration here is, yes, indeed, this expression appears, empirically to be a good recipe to determine the number E. And in fact, this is a definition of the number E, and you can show that it's equivalent to this definition here, this series. So, very interesting, this very odd number that, as I'll show in a later tutorial, is fundamentally the right base to use when you're doing calculus. It has many beautiful simplifying properties. And so in science, when you see expressions of this form, that number E is this special base, sometimes called Euler's number. Often it's called the base of the natural logarithm. And this is something that will make sense in 1 or 2 tutorials' time, because after this tutorial I'm going to turn our attention to logarithms, which are the inverse functions of exponentials. So one last thing, this number E is involved, it's a player in what's sometimes called the most beautiful equation in mathematics, and I think if you're told about the number E, you have to be shown this equation. If it has the name, the most beautiful equation in mathematics, then surely one must be allowed to see this, right? The most beautiful equation in mathematics. I'll put an exclamation mark after that, because that's quite a declaration, isn't it? Now this is, I think, a very good contender for the most beautiful equation in mathematics. It involves 5 absolutely fundamental numbers. What are those 5 numbers? Well, the first fundamental number in mathematics that's involved in this equation is the number 0. Any equation can be written as something on the left-hand side equals 0 on the right-hand side. 0 plays a very special role in mathematics. The next is 1, representing unity. The next number in this beautiful equation is one we know relatively well, which is pi, the irrational number that is the ratio of the circumference to the diameter of a circle, known to the Greeks. The next number in this most beautiful equation is the one that we've met today, Euler's number, E, which arises very naturally in processes to do with exponentials. I don't really have time to go into where this comes from in terms of compound interest, but that is something you can easily find on the internet if you're interested, and it's quite a beautiful example of how this equation naturally rises when you're thinking about banking, if banking could ever be regarded as beautiful. And then we have to say, well, what's the 5th number in this beautiful equation? Now, the 5th number is a number that you will only meet at advanced higher mathematics. But really, I believe every young person should meet this number early on in their maths career, because it is so important actually in mathematics and a little bit mind-bending. But this number is what is called I. And this I here represents the following. It represents the square root of -1. And that might seem a bit odd because you've been taught for so long that you can't take the square root of negative numbers. Well, you can't take the square root of negative numbers if you're dealing with real numbers. However, there's a wider group of numbers called complex numbers, and a complex number has a real part and an imaginary part, and I is the imaginary unity. So just as 1 is unity in real numbers, I is unity in imaginary numbers, the square root of -1. And it turns out that all of these 5 numbers are connected in an equation, which has the following form: e, so an exponential, raised to the power of I times pi added to 1 gives you 0. And that is a spectacular equation. You would meet this if you studied this branch of mathematics called complex numbers. But I think it's worth showing you here at the higher maths level. Even though we don't do complex numbers at higher maths, we do meet E, and I think it's beholden therefore for us to at least show you this extraordinarily elegant equation that relates what many would consider to be the 5 most sort of fundamental numbers in mathematics, that they're all related in a single equation. So let me leave it there. That's been, a somewhat theoretical discussion today, but about a very, very special number, Euler's number E, which has this value here. Approximately, it's an irrational number, has different representations, but as we'll see, it plays a fundamental role when we speak of exponentials, particularly when we think about calculus. So that's all for today, and we'll move on to logarithms in the next tutorial. So thank you very much for your attention, and I will see you next time.